All right, hello Chem 120 students. This is the first lecture of Chapter 4, and Chapter 4 is, I think, my favorite chapter in the book. That's hard to say, but it is a really good one. Okay, so, actually let me go back. This chapter is all about chemical reactions that take place in solution, that solution being water. So why are we so interested in solutions that take place in water? Well, because the vast majority of chemical reactions that allow for life to exist take place in water. So it's pretty important. And if you don't believe me, allow me to convince you. Okay, so you've seen this figure before. This would be sodium chloride being dissolved by water molecules. So water is known as the universal solvent, and we're going to see in a little bit, like 1 or 2 slides, why I have put universal solvent in quotation marks while your textbook has not. So here we have a great example of water acting as a solvent. So we have our many water molecules that are going to be interacting with this solid sodium chloride. So you can think of this as like taking a sugar cube, only it's a salt cube, and dropping it into a glass of water. So those water molecules are going to be bouncing off of each other, off of the container, and off of the sodium chloride cube. And in doing so, we're going to have these interactions between the positively charged side of the water molecule and our negatively charged anion. And then from our negatively charged oxygen of our water molecule and positively charged sodium. So we have these like charges attracting each other, and as a result you have them kind of like carrying away the individual atoms of our salt. So just really quickly, I know we've talked about water before in this class, but I want to hit on just a couple more things so that as we move forward, we have the same understanding of the water molecule. So here we have our oxygen, and it is, of course, bound covalently to our hydrogen, right? Non-metal, covalent bond. Now, if you look at your periodic table, which by now you should just automatically have in front of you, yeah, there it is, you'll see that there is a bit of a difference between our electronegativities in oxygen and hydrogen. It doesn't look as significant as it actually is, but we've talked about this from chapter 2 where we looked at electronegativity. You can think of hydrogen as being kind of nestled between boron and carbon in terms of electronegativity. So it's quite a few steps away from oxygen. Remember that oxygen, fluorine, nitrogen are our big electron hawks. So they're the most electronegative. Okay, so we have a difference in electronegativity between our hydrogen and our oxygen. What that effectively means is that there's going to be greater electron, that's an R, density around our oxygen, and there's going to be less electron density around our hydrogen. Now we're going to talk a lot more about this in chapter 7 and 8. We'll develop a much better understanding of our water molecule then, but I do think it warrants just exploring this a little bit now. So because there's greater density around that oxygen, what that's saying is that there's going to be more electrons there. We have a greater probability of finding electrons around the oxygen than around the hydrogen. Because of that, we get this kind of negative pull and positive pull to our water molecule. Now that charge is not a full charge. It's not an anion and a cation bond, right? This is not ionic. But it is enough of a charge disparity that you end up having our hydrogens with this slightly positive charge and our oxygen with a slightly negative. Now it is currently hydrating sodium chloride, and we can see it has full ionic charges between those chlorines and the sodiums. And our water molecule is attracted in the way that we would expect, with positive being attracted to negative and negative being attracted to positive. Okay, so why is that in quotes? Well, because if it is not a polar molecule, water will not dissolve it. So here we have oil, and we all know that if you took a glass of water and just decided that you wanted to add some olive oil to it, I don't know, why not? Do you? It would not mix evenly, right? It's not going to dissolve. So it's not going to be forming this like homogeneous solution, right? Instead, you're going to have this clear layer of your fats or your oil and your water. Why? Because oil is not polar, right? We have our sodium chloride. It has a difference in charge in it. Water can completely dissolve it. It's going to solve it. Here, that's not going to happen. So water is the universal solvent, but you need to always be keeping in mind that like dissolves like, right? So a non-polar molecule will be dissolved by non-polar molecules and not by polar molecules. And our polar molecule, sodium chloride, will be dissolved by water, but would not be dissolved by oil, right? You just have a chunk of salt in oil. You could try that at home, right? Enrich your life. Okay, so we use this like dissolves like all the time in our daily lives. So here we have a molecule. So right now I just want you to focus on this structure here. And we have this term hydrophilic and hydrophobic. So hydro means water, and phobic we can think of as being fear of or aversion to, and philic meaning love of. So water fearing and water loving. So this molecule that we're looking at is your standard soap. So here we have a hydrophilic region, and if you look, this is SDS, doesn't matter, sorry. So we have a lot of oxygens over here. Oxygens are really electronegative. They're going to be pulling electrons towards them. So this is going to be the polar end of the molecule. Right here it says the hydrophilic region. Over here, this is just a series of, this is like a shortcut way of drawing complicated organic compounds. And all of these are just carbons and hydrogens. Carbon and hydrogen are very close in electronegativity. Those are not polar bonds. They are covalent bonds that are pretty equal in distribution of electric charge. So they are not polar. They would be called hydrophobic. So you have this cool molecule where part of it is hydrophilic, wants to be around water, and part of it is hydrophobic. Well, wanting to be around water also means that it will associate with water molecules really readily. So that's that hydrophilic part. Hydrophobic part is going to try to get away from the water as much as it can, right? It's not attracted to it. So here we have a little fat droplet, and you can imagine that that is like a stain on your clothes. And what we have is this soap molecule, and there's tons of them in solution, right, when you add detergent to your laundry. And all of these hydrophobic regions, the regions that are not polar, are associating with that non-polar oil that's on your clothes. All of this hydrophilic region is associating with the water that's all around it, right? And it's doing so quite readily. And so what we have is this hydrophobic region is dissolving those fats, getting them out of your clothing, and then the association of your hydrophilic section, your water-loving heads, if you will, is allowing it to be carried off in solution. So that's what this figure, which is actually my favorite, it's from 2006, Good on you, Encyclopedia Britannica. Here we have dirt or oil on your clothes. You have your soap molecules. In red is that hydrophilic region. In yellow is our hydrophobic region. And it is associating, like I said, this is water, and blue all around it, that's the environment that it's working in. And so those fats or dirt get carried away. And that's the way soap works, right? That's cool. You can just share that at a party. And if you don't think that that is exciting, maybe you will get more excited by the importance of being hydrophilic or hydrophobic in the phospholipid bilayer, otherwise known as your cellular membrane. So remember, I said that most reactions that are required for life take place in water. So when you think of this as what it is, which is your cell wall, inside the cell is water. Outside of the cell is water. This is like that soap where you have your hydrophobic region. So this is our philic region, and those tails in the middle are hydrophobic. And it is because of this hydrophobicity and hydrophilicity that we are able to have selectively permeable cell membranes. What that means is that not everything can get through it, right? Thank goodness, otherwise it would be really hard for us to be alive. Okay, so that's my justification for studying water. Let's get on with the material for the chapter, shall we? All right, so this chapter kind of starts off by talking about electrolytes, which is something that we already explored in our conductivity lab, right? You watched that video that showed a light bulb being lit by different solutions and not lit by others. So now we can kind of, from that conductivity lesson, thinking a little bit more about ions, we can start to progress to think about chemical compounds as electrolytes. So the classification of an electrolyte is something that when dissolved in water will conduct electricity. So why does that happen? Because in dissolving, it is releasing charged particles into that solution. So being an electrolyte is a continuum. We have strong electrolytes, weak electrolytes, and non-electrolytes. And if you look at these strong electrolytes, you have this big classification here of ionic compounds. And I would just add the word soluble here, right? Because we're going to see that not all ionic compounds are soluble, but many are. So ionic compounds are just going to be any of our salts, right? Any of those compounds where we had our cation plus our anion. That's what they mean there. And again, not all of them are going to be strong electrolytes, but many of them will. The examples from the conductivity lab, like sodium chloride, I can't remember what else we were working with, are all examples of, I think you also had like potassium nitrate, are all examples of strong electrolytes. Other examples of strong electrolytes are going to be strong bases, as well as, hold on, I'm going to let that go away because it's ugly. All right, so here we have our strong acids. And we also have strong bases. All right, so what makes them have this like relative strength of being strong or weak? It's how readily they dissociate. So let's take hydrochloric acid, for example. In solution, when hydrochloric acid breaks down, you will find in that solution, if you were to look at 100 molecules in the solution, you're not going to find a single hydrochloric acid bonded together. So it dissociates really, really, really readily. That is true of all of the species that are our strong electrolytes. Weak electrolytes are those species that will release some charged atoms or components into the solution, but it's not going to be 100%, right? They're not going to completely dissociate. So an example of our weak electrolytes would be ammonia, right? So this is actually a weak base. Here we have our weak acids. Right, so this molecule here is our acetate, acetic acid, right? So if you look at your periodic table and you flip to the back and you find acetate, its chemical formula is C2H3O2, and it has this negative charge. So it's a polyatomic ion that we're already familiar with. The difference between acetate and acetic acid, shown here, is that this hydrogen gets pulled off into solution. Now, if you were to look at 100 molecules of our acetic acid, not all of them will have dissociated. That has to do with the stability of acetic acid versus acetate, which we will not get into, but Chem 2 you will a little bit, and if you take organic chemistry you will a whole lot. So it doesn't completely dissociate it, but you would find some that had. So there are charged particles in solution, and thus it can conduct electricity, but it will do so weakly. And that's what it's trying to show here. Here we have this really bright light bulb when we have many ions from a strong electrolyte. Few ions in solution is going to produce a low glow. And then last we have these non-electrolytes. So the non-electrolytes are really important just to recognize that, you know, all of these species are water soluble. Right, so what does it mean to be water soluble? It means that if you were to put a cube of sugar into water, it will dissolve. So it's going to form a homogeneous It forms a homogeneous solution, so it does dissolve, like still dissolves like, but no ions are released in solution. Right, so if you put sugar in water, you just have whole sugar molecules that break apart from each other, so it's no longer a clump of sugar, but you still have just those individual sugar molecules. Okay, so we're going to be talking a lot about solutions this chapter, so I just want to make sure that we have the same vocabulary. So again, a solution is a homogeneous mixture of two or more substances. We have this general definition of a solute versus a solvent. So the solute is the thing being dissolved. The solvent is the thing doing the dissolving. So generally we think of like having a glass of water, adding a little bit of salt. Salt would be the solute, the thing being dissolved. Water would be the solvent, and that would be true. But sometimes in chemistry it can be hard exactly to identify what's the solute and the solvent. For example, if you are adding two aqueous solutions, right? Whichever one is in the smaller amount is the solute. Whatever is in the larger amount is the solvent, right? Because that's going to be what is ultimately like the vessel that everything is being dispersed within. So solutions are homogeneous. Suspension would be as you start to see particulate come out. So things like solidify. You can think of that with the what's a good example? Oh, with our arsenic lab, right? So silver arsenate. When you first combine that silver nitrate with your arsenate, it is going to find each other, and some of it will start to precipitate. It almost looks like it's snowing. It gets kind of cloudy and gunky. That's a suspension. If you were to leave that for several days, then it would separate by density, and the precipitate would be at the bottom, right? We're already familiar with this term precipitate from our lab. Okay, so those are just terms that you need to know and feel really familiar with. Because we're going to be really focused on solutions, it's important that we're able to navigate concentration. So the concentration most frequently used in this course is going to be molarity. So molarity is represented by a capital M. And that capital M, it's kind of like density, where density stands for your mass over volume. Molarity stands for your moles of solute, so the thing being dissolved, by or over your liters of solution. So when we make a solution, one of the most useful tools is called a volumetric flask. So let's say this is a 50 milliliter volumetric flask. They come in a ton of different sizes, right? This would be our volume marker. So that would be at, if it's a 50 milliliter volumetric flask, that would be at the 50 milliliter line. You would add whatever it is that you're dissolving. So let's just stick with salt. So this is our pile of salt. We want a solution that's 50 milliliters. And so we would add our solid and then add water up to the top of that line. It is a very accurate way of measuring your solution, making sure that it is the exact right concentration. In contrast, if you needed 50 milliliters and you just took 50 milliliters and dumped in the amount of salt that you needed, you're not accounting for the volume of the salt. Right? So this is a really, really accurate way to go from a dry substance to an aqueous solution. Okay, so we're going to do just a couple examples of molarity questions because I think it's like deceptively simple, and students usually struggle with molarity a little bit. You really need to get to the point where when you see capital M, you know that it stands for mole over liter. Okay. All right, so we have a couple problems here. So what is the concentration of a solution prepared by dissolving 86.5 grams of potassium chloride and 750 milliliters of distilled water? Make sure that you are familiar with this abbreviation for distilled water, which is just DH2O. Okay, so when we say what is the concentration, we're in a chemistry class. We are interested in capital M molarity. What does molarity stand for? Mole per liter. Always, always. Okay, so right now we're given a mass, lowercase m, and we're given a volume. And we need to use that information in order to find our molarity. So the first thing we need to do is convert grams to moles. And there's only one way to do that, and that's molar mass. And at this point in the semester, you should be very comfortable doing that or making that conversion. So 86.5 grams of potassium chloride, right? KCl. Divided by our molar mass of KCl, which is 74.551. We get 1.16 mole of KCl. All right, so that gives us this first thing that we need. Now we also need to convert our volume to liters. So again, at this point in the semester, you should be able to look at 750 milliliters and just immediately say, okay, that's 0.75 liters. Molarity is mole over liters, so I have 1.16 mole of KCl over 0.75 liters. Plug that into your calculator, which you should have right next to you, so you can double check my work. Let me know if I'm ever wrong, which will happen. You have 1.54 molar KCl. Okay, so it's molarity. When we say this, I would say it is 1.54 molar KCl solution. Right, so you have moles, you have molar solution, or molar, and you have molarity. Yes, we love it. Okay. So that's one example. We're going to do one more. So what is the concentration of ions in 500 milliliters of a 2 molar solution of iron 3 sulfate? Cool. Let's go with purple for our color. Okay, so we have 500 milliliters, 2 molar iron sulfate. Question is concentration of ions. Right, this can be a really nice way to break up a question if you don't like word problems. Kind of get your pieces, box your question. It's a really helpful strategy. Okay, so our volume is 500 milliliters. We know we're working with molarity, right? So I know I'm going to have to convert that to liters. So I'm just going to go ahead and do that. My molarity is 2.0 molar. And it's iron 3 sulfate. So if you thought you were done with naming, oh, you're so wrong. It's the rest of the semester. So iron 3 sulfate would be Fe2SO4 3. Okay, so we need to figure out what's our concentration of ions. So in order to answer this question, you need to be able to look at that compound and say, iron sulfate is an ionic compound. Ionic compounds, there are some exceptions which we will learn about in our next lecture, but ionic compounds generally dissociate into water. This one does. So Fe2SO4 3 is solid, right? It's placed into water. Sometimes we'll write H2O under the reaction arrow to show what's happening in that chemical reaction, what's changed. It's going to iron, right? And that's 3 plus, and I have 2 moles, right, from my subscript, plus 3 SO4, which is a -2 ion. So that is what's actually happening when my species is going into water. And that's going to be kind of relevant in our lab this week, looking at stoichiometry. Okay. So now I can kind of visualize what's happening in my solution. So from every 1 mole of my iron sulfate, I get 2 moles of iron and 3 moles of sulfate. So I'm going to use that information and the fact that molarity is mole over liter in order to figure out what the concentration of my ions is. Okay, so I want to figure out how many moles of my iron sulfate do I have. So I want to isolate moles on one side of the equal sign. So molarity times liters equals moles. This is brilliant, and you're going to love it by the end of chapter 4, because it means that you don't have to look at molar mass. Yeah, right? We've proven ourselves. Okay, so we have a 2.0 molar solution times our volume of 0.5 liters gives us 1 mole of Fe2SO4 3, and that is in our 500 milliliters of solution. Okay, So now we want to answer the questions of, okay, what's our concentration of ions? Well, if we have 1 mole of our iron sulfate, I know I have 2 moles of iron and I have 3 moles of sulfate. So I have 2 mole of and I have 3 moles. So if I want to know the concentration, that's going to be in molarity. So 2 moles of iron divided by my 0.5 liters, right? 2 divided by 0.5 is the same as multiplying by 2. So 2 divided by 0.5 is 4. So that means that I have 4 moles. Oh, sorry. I have 4 molar Fe3 plus. Over here, divide that by 0.5 liters. This would be 6 moles of SO4 2 minus. Pretty cool. So there's a ton of problems like this in your recitation packet. Make sure you get some practice so that you feel really comfortable. Really need to get to the place where when you see capital M, you're like, oh, got it in the bag. I know exactly what that means. I know how to rework it. Most often, you'll take your molarity times your liters. You could also take mole over molarity equals liters. Okay. So the last slide for this lecture is looking at dilutions. So in the chemistry lab, we don't have a whole bunch of like pre-made solutions at different concentrations. So for instance, in my lab, we do a lot of analyses that require ethanol. So we only carry 99% ethanol, right? So that is a very high concentration of ethanol in our stock solution. But my working solutions, the solutions I'm using for experiments, are usually like 5% ethanol or 10% ethanol. So that's just a standard in chemistry. You save a lot of money, you save a lot of shelf space. All labs are smaller than you want them to be. And so we have these concentrated stock solutions and we dilute them to make our working solutions. And the most helpful formula I have ever learned in my life, I use this every single day in the lab, is M1V1 equals M2V2. So another way of writing this is, my mouse has been super touchy today, I'm sorry, is C1V1 equals C2V2. You might have seen that in a biology class where C equals concentration. Right, these are the exact same formula, only we're interested in the concentration in molarity. Right, because we're in a chemistry class. Yay! So here we have a concentrated stock solution. We dilute it, and this would be our working concentration. Another way of thinking about this is what you have. You have this really concentrated solution. This is what you need. And how you get from here to here is with this equation. All right, so let's do just one quick example. Simple equation, we got this. Okay, so how do you prepare 100 milliliters of a 0.1 molar sulfuric acid solution from a 2 molar stock solution? Okay, so a good way to kind of divide these up is to say like stock solution versus your like needed solution. So you're always going to have your molarity and your volume. So my stock is 2 molar. What I need is 0.1 molar. I need 100 milliliters of it. So I'm going to take my stock, I'm going to add water to get my diluted solution. So the question is, how much stock do I need? And then how much water do I add? Right, so I use M1 V1 equals M2 V2. My stock versus what I need. So I'm solving for a volume, so I'm just going to call this my stock side of the equation and this what I need. So if I'm solving for volume, I'll divide both sides by M1. M1's cancel out, and I get V1 equals M2 V2 over M1. All right, so now it's just plugging in those values. Now notice molarity is moles over liters. Let's just go ahead and change it to our, let's change 100 milliliters to liters. And place that over our 2 molar solution. Plug that into your calculator and you're gonna get, I hope I didn't do it that way before. 0.1 times 0.1 equals 0.01 divided by 2. You get 0.005, which is the same thing as saying 5 milliliters, right? Because that would be in liters. Now, if you hadn't changed to liters, you would get 0.1 molar times 100 milliliters divided by your 2 molar. Because your molarities cancel out when you divide, right? Our units cancel. It's okay that that was in milliliters. Now, the reason why I didn't model that at first is because if you're doing problems like those up here where it's not going to cancel out, you 100% need to convert milliliters to liters. Otherwise, you will get the wrong answer. So once you get to this point and you're doing dilutions, you can be a little bit more free with your volumes. Right? Just check that your units cancel out, and remember that capital M is moles over liters. They're canceling each other out. I'm left with milliliters, and you would just get 5 milliliters. Okay, so what does that mean? That means in order to make my needed solution, I need to take 5 milliliters of 2 molar sulfuric acid, and to that I need to add 95 milliliters of distilled H2O. So it is not enough in these problems to just say like, oh, it's 5 milliliters. No, you need to know what that means. That's 5 milliliters of my stock, right? That was the X that I was solving for. To that, I need to add water because the whole function of this equation is to perform a dilution, to get that solution that you need. All right, that's it for this lecture. So get some practice, and I'll see you next round.